We'll talk about typically needed data for various types of simulation projects. Over the years and here at PMC, I've worked with projects in manufacturing, warehousing, call centers, customer service, healthcare, and there's many commonalities among data you're going to need and the dangers in collecting the data or being unable to collect the data. We'll talk about that too. And potential pitfalls in interpreting the data versus misinterpreting it. So here are some of the more common pitfalls. All of these I have seen and corrected in various projects I've been involved with over my 35 years in simulation work. I'm old and wrinkled. You can't see that over the telephone, but that's about half my lifetime now, simulation work. Now, number one occurs often in manufacturing. The operator loads the machine, presses a button, and then can be and should be doing other work. And the simulation analysis needs to take that into account. Then the operator comes back after the automatic portion of the cycle and unloads the machine. If that subtlety is ignored, the potential throughput of your process will be underestimated. Number two can create over-optimism. The help desk support person gets there at 9 o'clock, but probably won't answer the telephone right at 9 o'clock. Turn the computer on, wait for it to boot up, put the microphone in. Maybe it's 9:04 before help desk service actually starts. Number three is very important for modeling downtime. Downtime urgently needs to be recorded. How long did the downtime last? And then how long after the repair did the machine run before the next downtime? Even a very short downtime, maybe the one in number three was 45 seconds, but it still should be recorded. Number four, this is one I've seen often in healthcare. The nurse, much as he or she might want to, nurses are typically very motivated to help people, but they also have to keep a logbook. The second patient might need medical help too, but the nurse has to make entries in the logbook so the doctors know what's going on between helping patient A in one hospital room and helping patient B in another. Now, for all these and many others like them, observe closely. As Yogi Berra famously said, you can observe a lot just by watching. And talk with the people who are actually out there doing the work. Not just the managers, not just the client interface. Go get with, look at, walk around, chit-chat over coffee with the people who are actually getting the work done. Then you'll become aware of subtleties like these. Now, I've already made allusion to downtime data. And the third point, the previous slide, was record all downtimes even if they're very short. And when modeling downtime accurately, these are questions that need to be considered. Second one here, begin at any time, or is the machine always working when it suddenly fails? And if downtime begins while the machine is working on a part, does the machine finish the cycle? And even if it does finish the cycle, does it ruin the part? Maybe we can repair it, maybe we have to scrap it. That needs to be recorded. Now, how long after the machine comes back up, how do you model how long before the machine has another failure? That may be best measured by, for example, how many holes does the drill press drill before the drill bit gets dull again? How long does the battery last, whether the vehicle is in use or not, before it goes dead? The polishing machine. How long is it busy polishing before the abrasive needs to be replenished? Those are 3 examples of each one of mean time to fail, or mean cycles to fail. Now, the machine might fail in several different ways. Could it be down and undergoing 2 different repairs at the same moment of time? Maybe not. Maybe one type of failure cannot possibly occur when the machine is already idle or under repair or turned off to repair some other failure. And work is likely to back up behind the machine that's shut off for downtime. Well, for how long before somebody sends the work elsewhere or lets it pile up or calls in a subcontractor or whatever? That question needs to be asked and answered. When a down machine creates a big pile up behind it, eventually something's going to give way or happen. What is that something and how soon will it happen? Now, the Hawthorne effect, if you breathe down people's necks and they see you right there watching, there you are with the clipboard and the stopwatch. Industrial engineers like me are notorious for that. How are they going to work differently? They might work faster to impress you. They might work slower so the productivity standards won't be set too high. Too high might mean higher than they'd like. This is named after, I've given this citation, it's actually named after a factory, not a person, but it's well known in industrial engineering. Now, first of all, how do you mitigate this? If you have to observe the work, you can't really get rid of it. But explain to workers there's going to be IEs in here looking at the operation to improve it. We need to improve it. We need to keep the business healthy. This is what's going to happen. We aren't building up a blacklist for firing. Observe as unobtrusively as you can, not right breathing down someone's neck. And to the extent possible, if you automate the collection of data, then you don't need quite so many workers, stopwatches, clipboards, and the psychological intrusion will be less severe. But it will still be there. You still need to be aware of it. And another precaution that can be taken is there enormously more or less production on the day you observe the work versus other days in recent history. And if there is a big difference, the Hawthorne effect was probably unusually severe and needs to be accounted for. Now, if you restrict data collection time, and sure, the warehouse runs all night, but I don't want to get out of bed at 11 at night, observe all, and then try to go to sleep the next morning, so I'll collect during the day. Well, that's a very human, natural attitude. I've got it myself, like my regular bedtime, but these are some of the pitfalls. And I've spent nights in the warehouse and then tell the boss I'll be in at noon the next day after getting some sleep. And these are some of the reasons. You collected data on one day of the week, but the workload was much heavier a different day of the week because of whatever. The second bullet on here has a reason connected with healthcare, the project I helped with not too long ago. There can be a big correlation, particularly in factories I've found over the years. The day shift is more desirable. Workers typically want it. They like the night shift less, and they like the evening shift even less. So, to be fair, the workers with the lowest seniority get the shift that's the least desirable. Well, they have the lowest seniority. They've had less training. They have less experience. They work slower. They make more scrap. They make more mistakes. That's part of learning. But the data are going to be different. Now, I've helped model filling stations and those oil change drive-in repair shops. And sure, it's nice if you have to be outdoors to collect the data, find a nice sunny day, temperature in the 60s, but the data may be very different the day of the bad rainstorm or the brutal cold or the snowstorm. But maybe data behavior that on those bad days, bad weather days, is very different. You'd better be aware of that. And the last bullet point on this slide is almost more clipboard related, like two different people pushing the pencil. We had one task, maybe it was a machine repair, maybe it was a changeover, maybe it was reloading a supply bay. That task took 25 minutes. But if we don't look at the data carefully and put those two clipboards together back at the office, it's going to look like 2 data points, not 1. And that's going to foul up the data analysis if you don't catch it. Correlation, who's he? I don't remember meeting Mr. Correlation. It's very easy, temptingly easy, dangerously easy. You have 2 data sets. You analyze one before lunch, get a nice distribution or histogram of the data, go to lunch, come back after lunch and look at the second data set. And you already modeled the first data set into the simulation model. And these are 2 examples of many. I've had to, watch out for this before the project had trouble. And one happened at the Quick Lube station. That was a project not too long ago. They're positively correlated. Bigger vehicle, more oil to drain out, more brake fluid to drain out. And if the positive correlation is there and not accounted for analytically in the simulation model because it was overlooked, you're going to overestimate your typical system performance metrics. Now, less common, but I've seen it happen, and here in number 2 is exactly how it happened. There is negative correlation. The system actually worked a little bit more smoothly than might have at first been predicted. So always check for correlation. Put the 2 data sets in 2 adjacent columns in Excel. Look at a scatter plot that takes only 2 or 3 mouse clicks. Calculate the correlation coefficient. That's another 2 or 3 mouse clicks. If it's not near 0, look for why there might be correlation and model that correlation in the simulation model. It's not hard for the modeler to do once the situation is given attention. Now, eventually you're going to get a nice data set, bunch of numbers written down in a spreadsheet or on a sheet of paper to be keyed into a spreadsheet. And ideally, you'll be able to find an appropriate distribution like the Erlang, the exponential, the gamma, the Weibull, that is a good fit to the data. And if such a distribution can be found, by all means, you'll have much more mathematical power for the simulation output analysis. Very rarely, and I had one boss a few years back who had a PhD in operations research. He knew what he was talking about, and he actually used the word never. And I have yet to find an exception about the normal. Now, if you use a uniform, say from 3 to 7, do you really mean it could never, never, never be smaller than 3 or longer than 7? Now, careful. Now, the triangular distribution also has hard end limits, same caution, and it has been popular for many years, including with me. There's the fourth bullet point. The triangular can be very appealing because talking with a non-technical person, it's very easy and productive to ask, what's the shortest time you ever need to do this task when everything goes right? What's the longest time you find yourself needing to do it on a bad day, when Mrs. Murphy is joggling your elbow? And what's the most common length of time it takes? And then you put those into a triangle. But it also has absolute bounds. And recently, at conferences I go to, analytical people are more and more saying, well, be careful of a triangular, its tails are too fat. And when you bring in a distribution like a gamma or a log normal, you can get rid of that objection, if indeed it's an objection. Exponential implies complete independence of events. That's often very good for cars arriving at a toll booth or incoming calls to a call center or a help desk. It's rarely appropriate otherwise. Now, other distributions, Gamma, Erlang, and Weibel, they can be very valuable. They certainly deserve examination in many cases. Now, suppose your data are bimodal. Put the distribution fitter aside if your histogram looks like this. I guarantee you, if you put those data into a histogram, and this is real data, got it right out of Project X, confidential, but that's where it came from, you won't find a distribution to fit. The beta distribution is one of the very few that has two peaks if you put in certain parameters, and then they're at the left-hand end and the right-hand end, not like this. Ask yourself, I thought I had one data set. How come I've got two data sets? Surely I have two data sets. I just didn't know it until now. Well, here's how you could end up with two data sets. You're going to separate your data using ideas like these, and then you're going to fit each distribution separately and use them both in the model. For example, you do some more digging, some more fact-finding, some more questioning, and the clerk tells you 80% of the time I can process the data quickly. But about 20% of the time, it arrives unsorted, and that takes me quite a bit longer. You take the two distributions, fit them, put them in the model, use one 80% of the time randomly, the other 20% of the time. Second bullet point, you need to look into your product mix. What percentage of your products are the deluxe model that need longer for drilling the holes or whatever? And do they come in batches or randomly mixed or whatever? The third bullet point, already discussed. We talked about downtimes. Fourth bullet point gets into pedestrian modeling. And we're doing quite a bit of that these days with cruise ship terminals, airports, physical therapy clinics, that sort of thing. The walking time may be very different. Number 5, you need to look at your absenteeism and what percentage of the time is only one worker on duty when there should be two unloading the truck together. So in all cases like this, collectively, this is what you do about it. Go back where you got the data. Look, I graphed it. How come it has two humps? It looks like a camel. And then you subdivide the data set. After you subdivide it, you fit each one individually, use those distributions. How often do you use each one? That's proportionate, and you put logic in your model to decide that. Oh, but we don't have any data. And ironically, that comes up most often when simulation has the potential to add the most value. The really valuable distribution simulation projects, the ones that I've seen return 100 to 1, as opposed to 5 to 1 or 15 to 1, those are the projects done to get rid of design errors while the factory or the warehouse or the hospital was still in a drawing on the back of a cocktail napkin, goes the proverb. Then you're going to have to estimate. Ask for expert opinions. After all, the proverb says expert advice is available from everyone. Opinions in the plural. Ask multiple people. You might have some history. Use that. You might be able to get a trade press magazine. That's the magazine actually used for some estimation, sanity checking of estimation in one of our projects second quarter this year. And most of all, sensitivity analysis. You may have 4 different possible values of a key number. You don't have any data. Which of the 4 values is correct or closest to correct? You don't know yet. Run your simulation with the 4 different values one at a time. That's like a high-powered version of the scenario manager in Excel, if any of you out there have ever seen that. Compare their results. Then you can find out, a tornado chart is good for this, which uncertain piece of data makes the most difference in the results the simulation model predicts. Concentrate your subsequent data collection efforts on those pieces of data. And additionally, and this is one I've sat in on at the table, number 2 arose particularly with downtime data. We didn't have downtime data on behalf of our client for the new $400,000 machine they just might buy. Well, we used some history. The old machine the client was thinking of replacing had 10% downtime. And the client was negotiating with a vendor, 2 different vendors, who both said, oh, our new machine is going to be much more reliable. It will have only 2% downtime. We ran the model with both numbers. Big difference in productivity. So we told the client, this vendor's promise is vitally important to you. Have meetings, separate negotiations with each of the potential suppliers of this expensive new machine. And we'll be at the table if you like, and we will explain that the 2% downtime you claim is vitally important to our client. So we're suggesting a contractual clause of indemnity if the machine is purchased and does not live up to that expectation. And one potential vendor said, oh, I have to go back and talk with the lawyer. The other potential vendor said, we'll agree to that. We've torture tested the new machine under adverse conditions, and we're confident in our claim. Well, after those 2 meetings, our client knew which vendor to buy the machine from. Leverage and contractual negotiations.